All right, my friends, today we're going to take a look at a super important, super useful topic, something called motional EMF. And again, this is this idea of where you can generate electric currents if you don't have a battery. So for example, what I've got here is this loop of wire, or coil of wire rather, connected to an LED. I don't have a battery, but what I do have is a magnet on a stick. And so what I'm going to do is put the magnet near this coil, and then I'm just going to spin the magnet. And you can see this light coming on. And the idea is why that's happening is because I'm changing how much magnetic field is punching through these coils, and that's inducing a current to run in the coils. So again, what's called motional EMF, it's voltage that you generate that drives current that you create basically by moving conductors through magnetic fields. So we're going to be moving this. In this case, I guess I'm doing the opposite. I'm moving the magnet in the presence of the conductor, and that's inducing currents in the conductor, right? So we're going to take a closer look at that. So a little bit easier to follow situation is one of these cases where you have a conducting, like a square frame, or rectangular frame rather, of metal, and you just pull it into a magnetic field, okay? And so we're going to kind of take a look at what happens when you pull a completed loop of conductor through a magnetic field. Again, the topic here is what's going to be called motional EMF. Again, all this is, what motional EMF is it's voltage generated basically by pulling conductors through magnetic fields. Through magnetic fields. I'm going to say mag fields. So again, whenever you see EMF, you can immediately think of that as voltage, okay? So the symbol for EMF is often going to be like this, but when you see it, it's really just a voltage difference, or V, okay? So here we go. It says the loop shown has a resistance of 6 ohms, okay? So this thing's going to be a big 6 ohm resistor. And we're pulling it to the right with a certain velocity. It says 5 meters per second. So somebody's just yanking this thing into a field. And it enters the field, and right when it enters the field, we're going to start our stopwatch, okay? And so the first thing it says is to draw the direction of the induced current as you pull this thing into the field. Okay. So realize what's being shown here is this region of space has a magnetic field going like into the board, right? I've made this kind of artificially large, everything here, just because I wanted to have simple numbers for some things. But great big region of space has a pretty large field, and we're pulling an absolutely enormous wire frame through this thing, right? So first it says find the direction of the induced current. There's 2 ways to think about this. Number one way of thinking about it is by looking at flux, okay? And so what's happening is, as we pull this in, we are capturing more inward pointing magnetic field. Okay, so one way to see what's happening here is we can say why the inward flux is increasing. Let's spell flux correctly. F-L-U-X is increasing. Now why is it increasing? Because we're capturing more and more field with this thing as it moves in. So the inward flux is increasing. And so what's going to happen then is the system will want to create its own outward flux to compensate. So the system creates outward flux to compensate. There's our symbol for flux. Okay, well then you think about, well, how would I make outward flux? Well, this thing can either run current, well, clockwise or counterclockwise, and it turns out if it runs the current counterclockwise, if it runs the current like this, current being the direction of flow of positive charge, then you would generate an outward field in the middle of the loop, generating outward flux. So you'd say, well, therefore, it's going to go, what is this, counterclockwise, CCW. So you can make the flux argument. You're increasing the inward flux, and so the system will try to make outward flux, counterclockwise current. Another way to do this is to actually think about the charges that are in this wire, okay? If you imagine the electrons, let's say. You know there's free electrons in conductors. And so what's happening is we'd be pulling that electron to the right through an inward pointing field, right? Well, so you can do with a negative charge, you could do like a left-hand rule, let's say, to figure out which way the magnetic force would be. You're pulling a negative charge this way through a field that points into the page. That's going to generate a magnetic force on negative charges this way. So negative charges would want to flow like that. Okay, so that's your direction of the electron flow, right? Or if you want with positive charges, if the positive charges were the things that were moving, which of course is the direction of current, you'd use like a right-hand rule. You'd say positive charge moving this way through a field that points in would feel a magnetic force that way. So this would be the direction your F magnetic on a positive charge, right? So that would drive current running around this way. So it's all kind of consistent. You can either make a flux argument, or you can actually just look at the magnetic force on individual charges where electrons get shoved this way, which makes conventional current go that way. So it's all consistent. Physicists got a pretty tight story on that one. So there's the direction of the induced current. It's gonna go around like this. So there's our current. Well, now we're gonna get greedy, and this is the essence of what we're about to do today. Is we've previously seen how to figure out which way the current goes. Now we're going to get greedy and figure out how much. How do we get how much current? The key thing to think about is, well, if I'm given a resistance and I'm being asked to find how much current, well, I'd like to know what voltage is driving the current. Well, we don't have a battery, so something's taking the place of the voltage. And what Michael Faraday figured out is the amount of voltage that's created by doing such a thing is you just need to find the rate at which the magnetic flux is changing. Okay, and again, right at this instant when this picture's taken, there's some flux because there's field captured by this loop, but as the loop moves, it's going to capture more and more. So let's play around with this. So the amount of voltage that we generate, we just need to find the rate of change of flux. So we already found the direction, so I'm not going to worry about the sign of a voltage. I already know which way the current's going to go. So the voltage that's generated is really, I just need to find the magnitude of the change in flux with time. Again, I'm not going to worry about sign. We already know which way things are going to flow, right? The negative sign is really just to remind you that the system tries to generate its own flux to oppose the change in flux. So that's what that negative sign's for. So I've already figured out which way things are going to go. So the voltage generated is change in flux with time. We have to remember what flux is. Well, flux is field times area. So we want to find the change in field times area with time. Well, when you see area, it's like, well, what area? It's the area that's in the field, okay? And so you notice if you look at the relevant area, right, this dimension of that area we called L, right? We're going to make up a symbol for this dimension. This is just, I'm just going to call this guy X. So that's the amount of, that's the width of this part of the loop that's actually in the field. So the relevant area is going to be L times X. So what we really need to get is the change in BLX with time. Well, if you look at these three quantities, the way I've got this problem contrived is the field, the strength of the field is just constant. And this dimension of the loop is constant. The only thing that's not constant is X. So you really get BL, which are constants, times change in X with time. Well, if you think about what this actually means, it just wants to know how does this quantity change with time? Well, that's really just telling you how fast you're going, right? Change in X with time. So this will end up being B times L times V. Okay, so what we've learned is in this kind of case where you're pulling a square shape or rectangular shaped conductor, let's say through a loop of or through a magnetic field, this voltage that's generated is going to be B times L times V. So let's just plug some numbers in. We have a 2 Tesla field, which is actually enormous. We have a very long length here. I made this thing, got a little overzealous with how big I made this, but I just wanted simple numbers. And the speed that we're pulling it with, what did I say? 5 meters per second, I think. Yeah, this speed is going to be 5 meters per second. So 2 times 3 times 5, 6 times 5. Turns out 30 volts. Okay, So what's taking the place of a battery is actually whatever is driving this thing or pulling this thing and changing the flux through the loop. And so that's going to drive current to go through this thing and perhaps make this, if it were a light bulb, come on. So we're changing the flux. If we wanted more current to run, we would change the flux at a greater rate, and so then we would pull even faster. You notice if you pull faster, that would go up. If you made the field stronger, of course it would, and if you made this loop even bigger than the enormous loop that it already is. So very, very important thing. And so then what you can do immediately after that is, if you have the voltage that's generated, well then we can just figure out how much current is running with Ohm's law. So if we just say, okay, well then V equals IR, the voltage we've got 30 volt difference, equals I times the resistance, I guess was 6 ohms, and so it looks like we would get 5 amps of current running through this thing. Right? And we already know which direction that current would go.